Okay, Sultan, you're on in three, two, one.
All right, welcome everyone to this IBIPS Education webinar. My name is Sultan Nagy. I'm a professor for building services at TU Eindhoven. Today we have a guest, Professor Nick Kelly, who will talk in a few moments about exploring a statistical model for EV charging for use with building simulation tool. And this is part of JBPS's special issue on exploring multi-domain simulation workflows for sustainable cities and communities. So like I said, this is part of the IBIPSA's educational committee, which is also what I'm sitting on. And so the idea is to educate and train the building simulation community, whether it's academia or private sector, to show the newest work, the coolest applications, the most awesome results. And that's why we're here. And hopefully we hear a cool talk also today. Everything that we do is online. You can go to the IBIPS University on YouTube, just as this talk will be uploaded shortly after we do it. This is the second talk of the series, so the first one's already online. You can go and check it out. And there's a few more to come in the next coming weeks, whether it's about digital twins, emission pathways, and then at the end we have Clarice, Laurie, and Camilla, who were the guest editors for this special issue, who will also talk about the impact of this special issue. Like I said, you can join us to make sure that you're part of the big growing community. And then you can also support us, become a member, get access to the journal, use the BIPSA logo if you want to, etc. All of that you can find on the website. And now I will stop sharing, and Nick, you can start sharing. And while you do that, I will introduce you. Feel free. So Nick, our speaker today, is a professor of energy systems at the University of Strathclyde, and he's also an IBIPSA fellow. He co-directs Energy Systems Research Unit, ESRU. He has been a researcher in the field of building simulation for about 30 years. His PhD work, which he still makes use of today, was on the integration of microgeneration into buildings and included development of a fabric integrated PV model, CHP component models, a dedicated multi-phase electrical load flow solver to handle power flows in and around buildings. His previous research projects include leading modeling activities in NX 42 and 54, which develop models for microgeneration technologies for building simulation. He led building modeling activities in UKRI's SuperGen, HDPS, high-def, and top and tail of energy systems, all focused on modeling and simulating future low-energy housing, featuring microgeneration and high-definition demand modeling. He also leads Strathclyde's engagement in the EU Ruggedized project, which trialed smart building technologies, and leading the UKRI FITS LCD project on modeling and testing fabric integrated thermal storage. He also leads thematic working group 4 on modeling and simulation in the UKRI Center for Net Zero High Density Buildings. Nick is heavily engaged in knowledge exchange, applying building simulation in areas as diverse as developing new business models for heating and social housing to mitigating methane emissions from cattle. He also set up the BIPSA Scotland USIM biannual conference series in 2018, which this year will be run jointly with the BIPSA England. And today's talk will actually use one example from the Ruggedized project that brings together a lot of his work in microgeneration, demand modeling, electrical systems modeling, and building thermal simulation. In his spare time, which I'm not sure how much you have, Nick, with all of these projects. In his spare time, Nick likes getting out into the Scottish mountains, cycling, running slowly. So with that, Nick, feel free to take it away. And while I'm sharing, one thing for the audience to know is you have a Q&A button. That's where we will record questions you have. Feel free to do that during the presentation, so that we can come back to it afterwards. So with that, take it away. Just let me know when.
So Zoltan, just to quickly check. So I don't think I've got driving control of the slides. So I'll just need to ask you to
Yep.
when we move forward. So apologies, folks. So these things happen when you're trying to do a live presentation. Okay, so firstly, thanks to Zoltan and Pamela for organising this little webinar. Hopefully, it should prove interesting to you. It's based on a paper that we produced for the Journal of Building Performance Simulation special issue, which was looking at EV charging. And how that was integrated into to building simulation. But probably a more useful strapline to that is looking at how we deal with behaviour-driven demand and also how we incorporate electrical energy into to building simulation. Because as we're all aware, in the sort of drive to net zero, the electrical side of buildings is becoming more and more important, be that through mobility, the transfer of heat from fossil fuels to electricity as well. So that's the kind of subtext for the talk. So if you could move on to the next slide, please, Zoltan. Excellent, thank you. So this is a little bit about the group I work in called ESRU. So we've been around for a long time, established in 87, but our work goes back right through to 1974. We've done a lot of work in sort of EU, IEA projects, but primarily our main area of expertise is in building simulation with the BRE Centre of Excellence in Energy Utilisation. And you may or you may not have heard of the modelling tool that we developed, which is called ESPR. So things like Energy Plus are effectively derived from ESPR. In fact, Drew Crawley, who led Energy Plus development a while ago, he did his PhD at ESRU. So that's our kind of background, very much building modelling and building simulation. Okay, so a wee bit of context to the talk. So the paper was derived from some work we did for Ruggedized. So Ruggedized was an EU project featured in 3 cities, Rotterdam, Emil, and Glasgow. And the whole idea was to test smart low carbon solutions. One of those solutions was this PV assisted electric vehicle charging, which was trialled in this glorious building here, which is the Duke Street car park in Glasgow. So that's the basis for the work that we're doing. So this modelling was effectively to support that part of the project. There's the paper. The paper draws actually on work that was done way back in the mists of time. There's an image of my thesis there. It shows you how many people have read it. But that was all to do with modelling of things like photovoltaics in buildings and electrical systems. But it also incorporates a lot of work from my researcher, who used to be a PhD student as well, Graham Flett, who does a lot of work looking at probabilistic modelling of demand. So that's the kind of foundation for a lot of the work that we're talking about. So on to the next slide, and thinking about what the sort of problem statement was. What was it that we were trying to address? So the key question coming from Ruggedized way back when it started in 2016 was, can PV with battery storage make a reasonable contribution to an EV charging hub in Glasgow? So the types of questions that we'll look at in this talk are, what's the contribution of renewable energy? What size does the battery need to be? What are the resulting power imports and exports? And as you'll see later, a little bit of a hostage to fortune. What are the emissions savings that we could look for as well? So next slide, Zoltan. So you're having to think about that problem. What does a model look like that you would need to answer that kind of question? Well, obviously, given that this is an IBIPSA presentation, we need a building model. How important that building model is a little bit of an open question. We need to augment that with information on a rooftop PV array. We need a battery model. We need to incorporate other loads, so lighting, heating loads in the building. We need to think about how we model EV charging, and then one of the things we need to pull all of this together is an electrical network. Okay, so if we could go on to the next slide. So thinking about the building model, first of all, so this was primarily developed by my colleague John Hand, who was very much architecturally inclined. So it's a very nice looking building model. So that was part of a kind of wider digital twin of the Duke Street area of Glasgow, which you can see there in the image in the top right-hand side. The car park model itself had an integrated PV array up on the upper floor. That was about 200 kilowatts worth of power output. It also included heating and lighting loads in the car park, mainly in the kind of stairwell areas. And it's not a traditional building simulation model in that we're not that interested in temperatures and whatnot in the bulk of the building. We're primarily interested in those electrical power flows. So the heating and cooling, which is normally our main focus in building simulation, is actually secondary in this model. Okay, next slide. So thinking about the PV array modelling, and this falls back on some of that older work that I've mentioned. So basically within ESPR, photovoltaics are an integral part of the building model. So you model a PV array just as you would do in most building simulation tools using a multi-layered construction. The only difference is you've got a special bit of that construction, a special layer which converts solar energy into electricity. The solar energy or the electricity is dependent on the amount of solar energy falling on the surface, and the heat balance is slightly different in that we need to take the electrical power generation away because that doesn't contribute to the overall thermal balance of the surface. But other than that, it's just a normal surface in your building model. You can see there in the if we can just quickly go back, you can see there on the car park model, you can see the solar arrays on the top of the building. So effectively, the ESPR model is you're modeling a single solar cell. You scale that up to the size of a panel, and then you can have multiple panels in surfaces. So you can have very large solar arrays modeled from a very small single diode electrical model. But it incorporates, so it allows you to couple the thermal side of things, so temperatures and solar radiation falling on surfaces, right through to the electrical generation of the panel. Okay, so next slide, please, Zoltan. The battery in our model here, it's being slightly flippant. It's a bucket model. So you have energy going into the battery, you have energy leaving it, you're tracking a state of charge. You've also got rate limits in terms of the amount of power that you can push into and take out of the battery, and then you need to account for losses. So there's conversion losses going into the battery, conversion losses going back out, and then you've got discharge losses in the battery as well. So all of that was incorporated in this model. Next slide, please. The hardest bit of work that we had to do was thinking about the vehicle charging and how we go about modelling that. So we were very fortunate in this project to have access to, at the time, which was a huge data set of vehicle charging information from Transport Scotland. So that was about 500,000 vehicle charging events. And that told you when vehicles charged, how much charge they took. It actually identified specific vehicles because people who had to charge had to tap a card, so it identified the vehicle when it charged. So there's a huge array of information that we could use from that to start to build up this what is a probabilistic model of vehicle charging. We got a later data set from Glasgow. That was about 2,000 charge events, which we needed really to update the model. It's a very fast moving area. The initial data set we had a lot of hybrid vehicles in it, and then slowly things began to transition to fully electric. So the difference between the two data sets was in the amount of energy that was taken in charges. So the Glasgow data set was really used to update our model. So what we used that information for was first of all to generate a set of probability curves. So we started off by saying, well, what's the probability that a particular vehicle will use a public charge point on a particular day? The other information we needed is what time is that vehicle going to plug in and start charging, and then we need to know on that charge event, how much charge is going to be taken. If you know the charger capacity, you can then work out how long that charge event is going to take. So we use that information to generate a set of probability curves, and really the charging model is just chaining those together and doing a bit of bookkeeping associated with the model as well. So next slide, please, Zoltan. So it's what I've termed a kind of vehicle-centric charging model. So you're tracking a population of vehicles, and then for each vehicle you're saying, is it going to charge on a particular day, and then tracking that through. If it does charge, what time does it start? How much charge does it take? We've got a lot of other stuff in the model as well. You set up a population of chargers, so you're looking at which charger the vehicle connects to, and then ultimately what you're getting out of this is you're getting an electrical demand for the charging hub. So by charging hub, I just mean a collection of chargers that exist at this Duke Street car park. The model validity was checked against the original data sets. So we split the data sets into different parts. So there's a calibration and a validation component. So the model is reasonably well validated, but against that, a data set that was of its time. And I'll come back to that towards the end of the talk, just to talk about how useful this model is in the present day context. Next slide, please, Zoltan. Okay, there's a sample of the type of output that you get from the model. So there's a set of power draws over the course of a year. It's fairly small scale there. You can see there that the power draws, they don't vary hugely throughout the course of the year, but you do get a degree of variability. So that's dependent purely on the probability of when vehicles charge. You can get other neat information come out of it. So that sort of green and grey diagram you can see there is charge point occupancy. So along the x-axis at the top, there's the individual chargers. The green boxes show you which vehicles connect to the chargers and when, and then down the side on the y-axis, you've got the time. So it's basically generating that charge profile, or the demand profile, but it's also telling you a bit about how heavily the different chargers are occupied as well. Okay, so on to the next slide. So a little bit of a diversion, so a little bit about probabilistic models and why we're interested in them, particularly on the electrical side of things. If you're looking at electrical demand, it's not like when you're looking at thermal performance, where you're maybe interested in sort of half-hourly or hourly. Generally, with electrical things, you want to look at sub-hourly, maybe even down to minutely. Because even minutely variations in electrical demand can impact on things, particularly these kind of tidal power flows, looking at where energy is imported and exported from a building. If you go beyond half hourly, you really don't get a clear picture of what those tidal energy flows look like. So a lot of the work that I'm talking about today is built on work that we've done previously, looking at these kind of probabilistic demand models for appliances, for electric vehicles, and then we augment things like normal heating demands, stick that on top of it, and you get a clear picture, not a clear picture, but you get a kind of high resolution picture of what the electrical demand looks like at household level right up to community level. So probability and probabilistic models are a kind of intrinsic part of looking at electrical power flows. Okay, so next slide. We can apply probability in lots of other areas as well. One kind of interesting one to point out is we're interested in what does EV contribute to our model in this case. And one of the interesting things is if you're going to look at kind of minutely demand for electrical power, and you've got an EV or a PV model, sorry, that's plugged into hourly solar data, there's a bit of a kind of discrepancy between the demand model and what you're producing from your EV generation. So we've also used probabilistic modeling when we're looking at solar data as well. Most of our solar data that we get in building simulation is hourly. We've used probabilistic models, so things like Markov chains, even sort of artificial neural networks to generate realistic solar profile. So the solar profile you can see there at the top right is kind of similar to what you would see in places like Scotland, where you get quite a cloudy environment. You get clouds drifting in front of the sun, sometimes all day, but sometimes for a few minutes. So you get quite variable solar input into the PV, and that gives you quite significant variability in your photovoltaic input as well. So we can apply these probabilistic models in the input to building simulation, as well as just looking at some of the demands. And then the one you can see there down at the bottom is hot water demand. So again, we've got probabilistic models that estimate hot water demand, and that work goes right back to IEA Solar Heating and Cooling Annex 26. So a lot of these probabilistic models, it's not just us, these are built on a lot of work from other people elsewhere. Okay, so next slide. So a little diversion there, but starting to pull things together. So we've got a model of our PV arrays on the rooftop. We've got a building simulation model, which is telling us about lighting loads and some heating loads in the building, which are electric. In this case, in the car park, direct electric. And then we've constructed this model of our charging hub, which tells us about EV demand. How do you pull all of that together? Well, the obvious way to pull all of it together is to plug all of these different electrical demands, electrical supplies into an electrical network model, and that allows you to track the flows into and out of a particular location. So the electrical network is the thing that's pulling everything together in the case of this model. So we get the PV array model generating time series data, hub model generating time series data. Our building simulation model is generating time series electrical data. So we basically plug this into electrical network model, and that tells us a lot about these tidal flows to and from our building, how much we need to import, what the battery is doing at any particular time. So this is the kind of nub of what we're looking at. So how do we use our electrical model? The simple way to do that is, for want of a better word, bean counting. You're plugging these things in, and your electrical model is tracking power flows over time. So the left-hand side there, what we've got is known as a one node or a one bus electrical systems model, and all that does is that just a Bayes rule, which is the summation of the power flows associated with that node or that bus is equal to 0. So what you're saying is what comes in has to go out, or is stored in the battery. And then on the right hand side, you've got sort of characteristic outputs of that model. So you get the generation from the PV, you get the load from the vehicle charging hub, plus what the building simulation model is telling you about the smaller lighting and electrical heating loads. The model's telling you at any point in time how much do you need to dump to the grid or export to the grid, how much is imported, so that's important because you're going to have to pay for that, and then what's the battery doing at any point in time. For the simulations I'm going to show you, the battery rules were pretty simple. Basically, if your PV output was greater than the demand, then you'd charge the battery. If the battery's fully charged, then that energy just goes to the grid. Similarly, if the PV output is less than demand, then the battery will discharge to support your EV charging. If the battery is fully discharged, so it's its minimum state of charge, then all of that energy would be imported from the grid. Okay, next slide. So that was a simple single bus or single node model. You could, if you wanted to, generate more sophisticated models where you've got multiple nodes or multiple buses. Say you're interested in tracking specific loads such as high and low voltage EV charging, you're maybe interested in looking at the lighting loads across different floors, then you could create a much more sophisticated model that provides you with more information. So you've moved away from that simple beam counting, so actually modeling a proper electrical network. And what that'll do is it allows you to track voltages round about your system. You can track power flows between your different buses or your different nodes. It gives you a richer picture of what's going on within your electrical network. The downside is you need to supply a lot more data, particularly for all of those components that exist in your electrical network, such as cables, such as transformers, and any power conversion technologies. With the model I showed you previously, you don't need to worry about that. You're just plugging everything in to a single node and tracking the flows. But again, the solution approach is the same. Every single one of those buses that I've labeled A, B, C, D, E, F, G, etc. All of those have to obey a power balance as well. Okay, next slide. So that sophisticated network model, we've actually got that embedded within ESBR. It's not used hugely, but it's been diffused into other tools such as Modelica, and I think Energy Plus has got a similar capability as well. Effectively what you do is you solve real and reactive power flows. You solve those iteratively. Interestingly, in ESPR, the solution approach we apply to electrical networks is exactly the same as we apply to bulk air flows. It's a Newton-Raphson iterative model, but this type of more sophisticated electrical network model allows you to do a bit more and get a bit more information back. So you can look at voltages, check whether you've got voltage problems in your system. You can look at power flows to and from the grids, and you can look at power flows to and from your different buses in the network. But it's a lot of work, and to be blunt, it's a kind of sledgehammer to crack a nut for the case that we're looking at. But it's just to flag up the fact that you can do these type of things. But for this particular example that we're looking at, that simple one node example is more than sufficient. Okay, on to the next slide. So in terms of the modelling, remember the original question was how well does PV support EV charging in Glasgow? It's very much a place-based analysis. So we're looking at this car park. A car park is a fixed roof area. The maximum size of array that we could get on the car park roof was 200 kilowatt peak. So we can't really change that. We want to maximise the amount of generation, but what we are interested in is what kind of size of battery do we need to support charging? What's the impact of different populations of vehicles using the hub? In terms of the simulation itself, we had to use 30-minute simulation time steps for this one. We couldn't go down to the sort of 5-minutely or minutely scale, and that was really just to do with the information that we had available for the model. So we're down at the 30-minute level, which can still tell you useful things about how the hub behaves. And the kind of things we're trying to extract from the model are, well, how much of the renewable generation from the array and the roof do we use? What are the energy imports and exports, and what are the power imports and exports? So what do the peaks look like, and how much impact does adding renewable energy into the mix actually have? On the left-hand side, or the right-hand side there, sorry, you can see the kind of things that we were exploring in the simulation. So we're looking at different populations of vehicles between 0 and 500, looking at the battery size, which was between 0 and 500 kilowatt hours. So the district, or the participants in the project, they'd set their heart on a 500 kilowatt hour battery. So we looked at whether smaller batteries would help you, and then we had a population of charge points that were already installed in the car park, so we integrated that into the model. Okay, so the next slide. So sorry about the typo in that previous one, but anyway, so there's our sort of typical output. So overall, we ran about 90 different simulations. So you had an annual simulation. You actually ran 2 years worth of simulation outputs, and the reason for that is you discard the first year, and that gives you a useful estimate of what the battery opening charge state is. So we used the second year of simulation data to do our analysis. So our output is generation. We're tracking the load from the EVs, looking at import and export, both in terms of energy and in terms of power, and also keeping a track of the battery state of charge. Okay, so that particular example was looking at a 50 kilowatt hour battery with a fleet of 50 EVs that would be using the charging hub. So looking at the sort of aggregate output, so that's taking that raw data and then generating some aggregate statistics. So the graphs that you can see here are the renewable energy contribution of the PV array on the rooftop. The different lines that you can see there are for different levels of or different numbers of electric vehicles using the charging hub, from 10 right through to 500. And then the x-axis there is just looking at the impact of different battery sizes. And really what that was showing us was that you don't actually need a 500 kilowatt hour battery to maximize the utilization of renewables. Really the sort of biggest bang for your buck comes at a battery size beyond about 200 kilowatt hours. Anything above that, really the gains from it are marginal. And also the renewable energy contribution, that is primarily dictated, or the ultimate contribution is just dictated by the number of vehicles that you have. With a large number of vehicles, you get very large energy requirements to charge your EVs. And because our rooftop has a fixed area and a fixed array on it, then it's a law of diminishing returns. The more vehicles you have, then the less contribution that array is going to make. We've got two different ones. There's renewable energy contribution, and then the other one is renewable utilization factor. So the renewable utilization factor is how much of that energy that you're generating on your rooftop actually goes towards charging those EVs. And that's an interesting one as well. Again, the larger number of EVs you have, the more of the energy goes towards charging them. If you get smaller numbers of EVs, then there are times during the day when you don't have any charging taking place, and that PV energy, or the energy from the rooftop, has to be dumped out into the grid. So that's two different metrics that we derived for this particular set of simulations. Next slide, please. The other ones are looking at imported electricity. And again, it's a kind of similar picture. You don't really need a very large battery to make the biggest difference on imported electricity. And the difference you can make is depends again on that size of vehicle fleet. If you get large numbers of vehicles, then you really don't make much of a dent on imported electricity with your battery and your PV on the rooftop. Smaller number of vehicles. Again, if you're going up to about 200 kilowatts or so in kilowatt hours in terms of battery size, then that's the kind of size of battery that makes the biggest difference to your numbers there. So that's really what the slide there is showing you. So there's not a huge amount of difference in the imported electrical energy, except for smaller vehicle sizes. And then in terms of the peak that you're importing from the grid, really your PV array and battery don't make much difference at all. And the main reason for that is that this is Scotland after all. In the middle of winter in Scotland, the amount of energy that's been produced by your PV array is pretty minimal. But you still have the same ongoing EV charging loads. People use their cars the same in summer as they do in winter. In fact, the load is slightly higher in winter because you get heating, you get more lights on in your car, so the draw taken in winter is slightly higher. So if the PV is not making any contribution in winter, you're having to draw all of that energy from the grid. So yes, PV and batteries will make a difference to your imported peak demand, spring, summer, and autumn, but in winter you're left with the same peak demand. So it's very much seasonally dependent. Okay, on to the next slide. In terms of the break-even point for this system, so if you look at what the rooftop array is producing, and you look just at EV charging, then your break-even point is about 100 vehicles. So the 100 vehicles over the course of a year, using that probabilistic model, the amount of energy that they consume is about equal to what's produced by the PV in the roof. If you take the other loads in the car park, so that's your heating loads, that's ticketing machines, your lifts, your lighting, then that break-even point shifts towards the left there, and you can support about 50 to 60 vehicles. So if you look at the overall electrical demand for the car park, if you include all the other loads, then it's about 50 to 60 vehicles that your array is going to offset. Okay, next slide. I did talk a bit about things like CO2 savings being a bit of a hostage to fortune. So you can look there, that graph there shows you the variation in grid carbon intensity in Scotland between the year 2000 and 2023. If you look at that, there's a very, very sharp decline around about 2015. Which is when the ruggedized project started. So when you got to when we were doing most of our analysis, which was in the 2020s, the amount of grid carbon intensity in Scotland was absolutely minimal. We're round about at the moment about 20 grams per kilowatt hour. So actually CO2 savings are fairly small for this model, simply because the carbon intensity of grid electricity is so low. So that's just a little warning about how things change with time. In Scotland, the grid carbon intensity collapsed, so carbon savings as a metric almost became meaningless. The other thing I mentioned was the fact that we calibrated the model on two data sets. So the Transport Scotland data set was collected between 2013, get this right, Nick, and about 2016. And then the Glasgow data set was 2016 and 2017. So that told us a load of useful information about how often charge points were used, how much charge was taken, when charging started. The only problem was that during that period, or just at the end of it, charge points in Scotland went from being free to the cost of charging at a typical car park charge point being 50p per kilowatt hour. If you charge your vehicle at home, then your off-peak charge is about 7 pence per kilowatt hour. So what happened was that because the price suddenly increased dramatically for public charge points, the demand for those charge points collapsed. And people started mainly relying on home charging. So all of those kind of nice statistics that we gathered for charge taken, when charges start, what the probability of a charge point being used, all of that is effectively redundant. The form of the model is still fine, but what we're now having to do is recalibrate that model with more recent data from Transport Scotland to reflect that change in price. So again, two hostages to fortune there: the actual probabilistic model itself, but also trying to compute CO2 savings in an energy system that, to be blunt, in Scotland is pretty much decarbonised already. Okay, so next slide, please. So just in terms of a few conclusions relating to the paper itself, can PV support EV charging? Well, the answer to that is yes. But the actual size of battery that you need was significantly less than was originally envisaged to maximise your renewable energy contribution. Below about 100 vehicles, that rooftop array is effectively offsetting most of the demands and has quite a big impact on reducing your imported electrical energy spring, summer and autumn, but not so much in winter. Can PV reduce your peak electrical demand? The answer to that is an emphatic no, because it makes almost no contribution in winter, and most of your peak power draws actually occur in winter, because when your lighting loads, when your vehicle requirements, your charging requirements are maximised, your PV can't actually contribute to that. So that was the answer. It's very much seasonal whether or not PV makes a contribution or not. And then the other interesting one is the fact that what's reported in the paper is not necessarily that time resilient. So EV charging is very much sensitive to charging costs. So again, with that situation in Scotland, where public charge point costs went from being free when with very few electric vehicles to 50 pence per kilowatt hour, far more than the home charging cost. So that's had a big impact on behaviour, and because our model is behaviourally driven, then we need to recalibrate that model for current circumstances. Okay, on to the next slide. Okay, so more general conclusion. So, the future of the built environment is electric, probably. It's a fairly slow transition, but if you look at what's happening in the UK and elsewhere in the world, there definitely is a transition away from fossil fuels. We need to start to think about the integration of localized generation into our models. So this one focused very much on PV, but I've frittered away a lot of my time in the past looking at things like micro wind. The reason why there's a crying with laughter emoji there is micro wind is a dreadful technology for urban areas. It contributes almost nothing in comparison to things like PV. But we also need to start thinking about heat pumps. EVs suddenly become an integral part of your building load, particularly if you're looking at homes and home charging. And then we've got all those other hybrid loads as well. Things like lighting consume electricity, but they also produce heat that also sets heat demand. So all of that we need to think about how we incorporate into our models. And the infrastructure is there in a lot of building simulation tools. We just need to start using it more regularly in our day-to-day activities. As I said, when we're looking at electrical demand and electrical generation, those kind of probabilistic or highly variable short time step changes in electrical demand and electrical generation start to become quite important, particularly if you're interested in looking at how supply and demand are changing with regards to the grid. So it's useful if we track those things at high resolution. And as I've said, a lot of the infrastructure to allow you to do this already exists in modelling tools. So ESPR, and not many people use ESPR, but it's a useful test bed for this. And a lot of what we've done has been adopted by Energy Plus. Some of the work that we've done was the template that was then used in Modelica. So it's slowly diffusing into the modelling world, but it's not used that frequently. And this idea of kind of behaviourally driven demands, particularly electrical demands, but also incorporating things like hot water, is very much a live research topic. So there's a lot of work going on, a lot of really good work going on elsewhere in the world as well. So it's as I say, it's very much a hot topic in terms of building simulation research. Okay, next slide. Okay, so I've got a slide up. I'll not go through that in any great detail. A lot of this probabilistic work that we're doing has been taken forward in a tool called Octem, which is available for download. The EV charging model is going in there as well. That was initially developed in VBA, then Python, and then it's moving into Octem. Okay, all of the sort of electrical and power flow modelling that I've talked about, that's available in the current version of ESPR. So if you're interested in that, there's a link to the download there as well. And a lot of the work that I've talked about in this case is being taken forward in a few large research projects in the UK. So one of which is Centre for Net Zero High Density Buildings. So that's very much focused on building refurbishment and transitioning buildings towards net zero. So the electrification of heat. So a lot of these models that we're developing are applied directly in that project. Next slide. Okay, time for a shameless plug. So a lot of the work that I've talked about, you'll see quite a bit of that in BSO USIM. So that's the joint IBIPSA Scotland, IBIPSA England conference, which is occurring in November. If you're at a loose end in November, please think about registering and come along to that conference. There's a lot of really interesting stuff going on in urban modelling and urban systems modelling, and you can hear all about it from that conference. The proceedings will also be available on the IBIPSA website at some point next year, I hope. Okay, next slide. Okay, so hopefully that's me kept reasonably to time. We've got about 15 minutes or so for questions. So thank you very much for listening. There's my email. If anything pops into your head after the webinar and you want to ask me a question directly, I'll be more than happy to try and answer that. Okay, Zoltan, so I think it's back to you.
Thank you, Nick. Thank you very much. I was very excited to listen to this talk. Like I said, for the audience, if you have questions, put them in the Q&A. There's 4 questions there. I also have a couple myself because I had very active listening sessions since I had to follow for the slides.
Okay, good.
So I listened very closely. But anyway, there are a couple, and let's go through them. So David asks, your modeling technique, basically as an extension, could you also simulate vehicle to grid or kind of a virtual power plant type operations?
Oh yeah, absolutely. It's really just a case of you need to identify what the rules are for the vehicle to grid interaction. So at what point can you discharge to the grid? There also needs to be a wee bit of foresight. So you obviously need to know, well, when does your vehicle need to be charged by? And there's interesting things you can look at. So if you're doing V2G operation, you can track the vehicle and whether or not the vehicle is ready to go at full charge at the leaving period. So you can track when your vehicle to grid actually starts to interfere with your ability to leave the house on a full charge. The other things that we've used this type of thing for would be looking at your flexible demand and heat pumps. So you're plugging your heat pump into an electrical network, you're tracking the electrical network state, and then if you're looking at, you get a collection of buildings, you get a transformer that's heading towards thermal overload, you can start to request that the heat pumps start to throttle back or actually stop using power, or if you get surplus power coming from PV and rooftops, actually bring your heat pumps on and use them to charge some thermal storage. So the whole range of applications that you can use it for. As I said, the main thing that we use, much to my annoyance, the main thing that we use the power flow modeling for is really just tracking bean counting of power flows. There's not a lot of call at the moment for that more detailed modeling, where you're maybe looking at the distribution network in a population of houses. It's very much most of the modeling that we do is the single mode or single node modeling. Yep.
Yeah, I think that answers another question here about if there's a plan to improve the control strategy to reduce grid congestion and grid dependency. So you say it's possible, but it's not currently being looked at, right?
Yeah, but it's certainly something that we as a community should look to move towards, because the sort of electrical modeling community, their models of buildings and loads are not as sophisticated as ours. So there's a kind of nice halfway point, I think, where our more informed thermal physics models can actually give them some really useful information on how they could go about managing their networks.
Yeah. Yeah. Okay, so here's one I'm gonna read because it's hard to congest. Let me see. So it's two part. The first question is, how do you ensure the consistency between arrival and departure time with EV energy demand and maximum power of the charger, since this may lead to incoherence in the EV peak demand?
So that was ensuring consistency between
Arrival and departure time.
arrival and departure time. Okay, yeah.
And the second
There was a
part
second part.
was, yeah, do you include the calculation of available rooftop area and optimal spacing between the PV cells for the PV production?
Right. So okay, so I'll deal with the first one. So what the model is doing is it's calculating a charge start time. You then plug the vehicle into a charger. So that charger could be, depending on the population we've got, it could be a 20 kilowatt, 22 kilowatt charger, 50 kilowatt charger, or there's some older 7 kilowatt chargers there as well. So what the model then does, it's not the most sophisticated, but the vehicle will plug in, and then it needs to wait until it's fully charged. So you've got a start time, you need to wait till it charges, and then you work out what the departure time is, or the disconnect time from your charger. So you're assuming that the drivers are relatively well behaved. When their vehicle's fully charged, they'll disconnect and then make that that charger available. So that's how you ensure consistency. There's no overlap. For example, calculating that a vehicle stops charging before it begins. So you're calculating a start time, charge, and then you've got an end time automatically from that one. Okay, so I hope that answers your question. It's not the most sophisticated of models. We have had a bit of work later on, which is we've got some data from our own university, which was looking at when do people actually vacate car parks, and then trying to integrate that into the model, but it's not finished yet, and it's a bit of work that needs to be done. The other part about the PV array on the rooftop. So very much the PV array design on the rooftop was a done deal. So we knew what panels we were going to have installed. We knew where the PV was going to be located, and that was dictated. It's quite hard to optimize because you've got to ultimately got to allow cars onto the rooftop as well, so you can't have PV necessarily everywhere that you would want it.
Mm.
So the PV design or the rooftop design was pretty much there. So we just took the information from that and we integrated that into our building simulation model.
That's even better than most projects, right? It's the actual design for the
Yeah.
panels. Um, so another question that came up here, which I was also wondering about, is the data that you used public domain, or is it something that is not possible to share, like the charging, or is it even relevant at this point? I mean, like you mentioned at the end, is a lot of the things have changed.
Yeah, unfortunately, that Transport Scotland data set, I mean, it's a fantastic resource, but it's not public. I
Mm.
will ask Transport Scotland whether it could be made public, because it is very, very useful to researchers. The statistical models that we generated from it, they are, I think, anything we derive from it is publicly available. And if you download Ocdem, or if it's not there, if you ask myself and my colleague Graham, we should be able to make that available to you. But again, it's that point about EV charging, or EVs and EV charging are very much a kind of it's a rapidly evolving technology, and all of that work, that nice work that we did to generate those probabilistic charge draw, charge start time models, all of that really was, for want of a better phrase, blown out of the water when charging costs went from 0 to 50 to 70 pence. Basically, that just you saw the demand on public
Mm.
chargers in Scotland collapsed, and then that demand moved to home chargers. So yes, the data would be nice to have, but it's very much a creature of its time, in that hyper charge demand behavior doesn't exist at the moment, and we really won't see it existing until public charge costs decrease.
Yeah, I think there's a question that I think is also answered by this, whether the model can be adapted for other cities. If I guess if the other cities have free public charging, maybe, but if not, then it's unlikely that
No,
it.
yeah, no, the model can be adapted for anything. It's, as long as you've got a data set that you can calibrate it with. So, that data set needs to include, when the particular vehicles charge, how
Mm.
much draw is taken during charges, and when the charges start. If you can get a stop time on it, fantastic. But you need that information, but you can calibrate the model, as long as you get a contemporary data set.
Yeah. So, okay, so these were the questions in the Q&A. I do have a few more because I'm very curious.
Yeah.
So for example, like you said, there's a shift, right? So there's not a lot of these public chargers available, and there's a lot of home charging available. At the same time, we all talk about solar and batteries in the homes, or vehicle to grid. So I wonder if you can almost just extrapolate your data set, or your results to what is possible in homes, or even in groups of homes, really, because that's kind of what this is, what you have, right? Other than the thermal loads in the homes, it's very similar, except maybe on the EV timing.
Yeah, no, you can adapt this particular type of model again to look at groups of homes. The only issue with that is effectively this model, it's almost kind of vehicle agnostic.
Hmm.
So when a vehicle comes into the charge point, plugs in, the model's creating this. Well, what's the load that's taken by this vehicle? So it's just using the probability curve to tell you what it is. Um, when you look at home charging, particularly if you're looking at individual buildings, those individual buildings, they'll have a particular vehicle type, so you can't use a kind of generic probability curve for charge taking, because that vehicle is going to have a specific maximum amount of charge that it can take. So we did do a bit of work in this quite a few years ago now, where you were looking at effectively diary data from individual homes. You were looking at the type of vehicle that they had, and you're almost customizing a model for that particular home type. So I think, yeah, this model could be applied to domestic charging if you got the data, but it need to be populations of buildings. And if you're really interested in the kind of interplay between your photovoltaics, your battery, and the EV for a particular household, you really do need household specific data. So it wouldn't be appropriate in those circumstances.
Yeah. And I will, as a good academic, I'll just make a comment on one one of your slides because I really enjoyed it when you said, like the market collapse or the model boundaries collapse when the price structure was or changed basically. And I see so much work that optimizes charging behavior based on pricing structures, and I think your work is extremely important as a warning that those results are extremely fragile because things can happen almost overnight, and then all the results go out of the window almost, right? If the pricing structures are changing, and which is why it's interesting to look more on kilowatt hours
Mm-hmm.
in flying rather than cents as a
Yeah.
primary optimizer because of this. But it was very exciting to see.
Yeah, I mean, the other argument for that one is if you optimize on things like carbon savings, because again, as the grid decarbonizes, carbon savings become less and less
Yeah,
important. You could see that from the data that we had from Scotland after about 2015,
yeah.
with the last coal-fired power station we had shut down. The carbon content of grid electricity collapsed. So the carbon savings that you calculated, didn't matter what scheme you looked at, the difference between them was really, really small. So as a metric, it almost becomes meaningless. And again, you need to go back and what are the parameters that are resilient that you can use for optimization? So it's energy, it's power, it's those kind of things, rather necessarily than those which are likely to just vanish or disappear with time.
Yeah, but on the other hand, also, I think the scope of the work or the system boundaries expand because yeah, you can say you don't save emissions, but at the same time, if your car's ICUs are substituted by EVs, you do save
Mm-hmm.
quite a bit, right? But your systems boundary changed.
Yeah, yeah.
So actually, it is an interesting development. And so in the buildings in simulation, you take that also into account, which is also fascinating. So maybe a closing question, because we have 1 minute left. And you talked about this a little bit, but how your loads of buildings become electric. But do you see a way towards adaptation of the typical building simulation tools that we have Energy Plus, and then like a workflow that to model the electrical part, which becomes more and more important. Like for those of us, I mean, for those who starting out, let's say, looking at it, what is the best way to think about this?
Yeah, I don't have a direct answer to this question because I'm not so familiar with what's actually in Energy Plus at the moment. But one of the key things that we need to do, and this goes right back to my PhD in the Stone Age and this last century. How old does that sound? But one of the things you've got to model are what are known as, I call them hybrid loads. But effectively, it's those things that exist in the electrical world and also our more comfortable thermal world. So it's looking at lighting. So you've got your lighting data structure. What you need to do is you need to expand that. So you need to know, well, what's the power draw of your lighting? What's the power factor? Because that becomes important as well. You've maybe get motors, pumps. You've got to include all of those entities within your modeling framework as well, and you need to populate those with the data that will allow you to go from our thermal predictions, our flow predictions, to well, what's the power draw of that pump? That then needs to be tracked by your modeling framework. So again, I mentioned this. I think a lot of the infrastructure exists, but it's whether or not the data exists for us to do that modeling. And that's really a sort of community request. It's to start gathering that data and start to make those not models. The models exist, but it's almost expanded models that include a proper representation of what the electrical behavior of those devices is as well. Final thing to point out about that modeling, the modeling that we're doing is predominantly load flow. So you're using
Mhm.
phasor variables. You're assuming that they are relatively stable over short periods of time. You're not getting into the kind of sub-second type modeling that the
Yeah,
electrical power flow modelers use, or the electrical engineers use. We're still very much in those kind of longer time frames. But
yeah,
for building simulation, a minute is quite a short time frame, but an
yeah,
electrical
yeah, yeah.
engineer that's an eternity. So there's very, very different time constants that the two communities are working with.
Yep. I think consolidating those two will be the next part of this journey, I think, for our
Yeah.
community. Well, Nick, thank you so much. I learned a lot. I think we all learned a lot. We're right on time. So as I said, the video will be uploaded pretty soon, as soon as we can. And then we can join us for the next edition of our WIPSA webinar on May 29th in the afternoon. Thank you very much.
Thanks, folks. Bye.
Bye-bye.